All right, number 6. Cylinder of mass 0.3, radius, tells us the eye of the cylinder placed at the long, tall ramp. So let's draw our picture. Right? So here's my cylinder. When it reaches the ground, so right here, it's rotating at a rate of, so that would be its omega equals 6.5 revs per second. Right? What is the linear speed at the bottom of the ramp? Well, part A should be really easy because I know angular velocity is 6.5 revs per second, but I need the right unit. So let me clean this up. I can convert to radians, so I put revs down here to radians. I know 1 rev is 2 pi radians, so I'm left with 13 pi radians per second. Now, how do we go from angular to linear? Well, I know angular times r equals linear. So 13 pi times r, which is 8 centimeters, so 0.08, you gotta have the right units, equals the velocity. So 13 pi times 0.08 gives me a linear velocity of 3.27 meters per second. Let's check, see that we did this one right. 3.27 meters per second. There we go. Let's now do part B. So part B, I cleaned some stuff up a little bit here, is what is the total kinetic energy? Well, at this location, at the bottom, what type of energy do I have? Well, I have KE plus KE rotational equals the total KE. So 1/2 mv squared, I already have that, plus 1/2 I omega squared. I already have I already have omega. This seems to be a simple plug and chug. Half the mass, my mass is 0.3. The velocity at the bottom, that's what we just calculated, 3.27 squared, plus half of I. Okay. I is 1/2 m, which is 0.3, times r squared, 0.08 squared, times omega squared, and that was 13 pi radians per second, and that has to be squared. Okay. So let's see what I come up with for this one. I ended up with 2.40 joules is the unit for energy. So hopefully in a lot of these problems you're seeing a lot of review pieces. Now, part C says, what is the height and the angle of the ramp? Alright, well, we know the length of the ramp. If this was our triangle, is 2 meters. If I can find the height, I should be able to find the angle. Well, how could I get height? Well, we talked about going from one height to another, you should be able to do conservation of energy. So let's say energy at the top plus work non-conservative equals energy at the bottom. We just said at the bottom it's only kinetic energy. And I already found that mathematically is 2.4 joules. The only forces is gravity, that's conservative. Rolling friction, which we said is also conservative, so that's not there. And then what type of energy do I have at the top of the hill there? Well, that is only potential energy, and potential energy is mgh. So mass is 0.3, g is 10, times the height equals 2.4. So I believe you have 2.4 divided by 3, and I get a height equals 0.8 meters. Okay. So that's 0.8 meters. If I was looking for the angle, the trig function I would use is sine of theta equals opposite 0.8 over 2 meters. And I get a theta of 23.6 degrees. Let's check. 0.8 and 23.6. Okay. Again, I'm always rounding these to 3 significant figures so you can see where you're at. Alright, the next one. What were the linear and angular accelerations of the cylinder down the incline? Well, this one cheated and it gave you a hint and it said use kinematics. So, let's clean up our work here. And whenever we do kinematics, we want to list all of our variables. So these two variables, I know omega final is 13 pi rads per second. Omega initial was 0. Other angular variables, I don't really have radians there, so I don't know that. So let's go to linear. Well, linear, I know the initial velocity is 0. The final velocity is 3.27 meters per second. And I know the change in x, or the length down the ramp, was 2 meters. Based off of these variables, I should be able to solve an acceleration. Doing this, I could do a change in velocity over time. You could do this problem 2 ways. To find the acceleration, you could use v squared equals v initial squared plus 2a change in x. Or you could do v average equals change in x over t. But then you'd have to do another equation, which is acceleration equals change in velocity over time. Pause the video and check and see what you get mathematically from that. Well, we keep coming down here to the answer. You should have gotten 2.67. Now, how could I have gotten angular? Well, I need another term. Well, remember, anytime you have the linear, you will also have the angular. So I could say linear equals angular times r. So 2 meters equals the change in theta times the radius, which is in the right unit, 0.08 meters. So 2 divided by 0.08, I get 25 radians. Then I could go back and I could use the same equations. Omega squared equals omega initial squared plus 2 alpha change in theta, or omega average equals change in theta over t, and alpha equals change in omega over t. Okay. Check for yourself. If you had to see what you got, okay, you better have gotten 33.4. Check and see what you get. Part F has us drawing the diagram, the free body diagram, on the ramp. So here's my ramp. Here are my forces. The first one, acting at the center, is gravity. Normal force. Okay. Normal force acts at the surface and it goes perpendicular to the surface. And then to make this roll, if it has a velocity this way, it better have a rotation that way. So then friction has to go up the ramp. Excuse me. Also making sure friction is at the surface because it is a surface force. So that was E. For F, draw the equations. Again, make the direction they go positive, right? Or they're rotating. So positive, we will say, is down the ramp. So what force is going down the ramp? Well, we've seen this joke before. What sends you down the ramp? That is mg sine theta minus friction, because friction's going up the ramp, equals ma. What's causing a torque? Well, there's only one force causing it a torque. We'll call that clockwise positive direction. So that is friction times the radius equals I alpha. So that was F for my second law equations for translation and rotation. Lastly, G, how much frictional force was required to prevent slipping? Well, that's solving for friction here. Well, we have multiple unknowns in this problem. I don't know friction, and I don't know alpha and A. So to get alpha and A, we put the non-slip. So then our angular equation now becomes F times R equals I A over R here. I, we can also plug that in. F times R equals I. Well, I got to double check what it is. In this problem, it's 1/2 mr squared. So 1/2 mr squared A over R. Hopefully you've paid attention to this math. We've done it again and again. All the R's cancel, so I have friction equals 1/2 ma. Problem is, I don't know F and I don't know A. But if I were to look at a couple of these, I don't know this. I have two unknowns, and I have those same two unknowns that I underlined there. So I can take this friction and plug it in there. Wait a minute, I'm looking for friction. So if this is the case, I don't have to do all this work. Okay? What can I do is I already have acceleration, so I can plug it in. Luckily, I could have done kinematics before, so this is much more simplified. So you could have done that top equation that's boxed, or now this bottom equation. I'm going to use the bottom one while I'm at it. So friction equals half the mass, which is 0.3, times the linear acceleration. I believe that got 2.67 meters per second squared. And you get 0.4 newtons. We're almost done. Okay. The last one we had left is if the cylinder were replaced with a hollow ring, how would that affect the acceleration? Okay. Well, I can look down here and see what affects the acceleration. Well, friction affects the acceleration. What would be different between rotating a cylinder and a ring? Well, we know that the ring is harder to rotate, and what rotates it? Friction rotates it. So you would have more friction. So if friction goes up, okay, your acceleration will have to go down. Right? So I would be looking at this equation. As friction goes up, your acceleration goes down. So you would get less linear acceleration. Okay. The next one there, we can already see that the force of friction to prevent slipping would have to increase. So I should have less and more. Okay? Making sure you can explain these, which we just did. Making sure you're studying for the test. Good luck.